Thank you. Okay. You got your Becca paper? Yeah, it says Becca on it. Right?
Then Ryan Becca.
Yes. And this is one that I have a messy, I didn't redo it several times, so. Okay. What I need you to look at on this problem, though, is in the beginning we've got 2NO plus Br2 goes to 2NO BRs. Okay. And then also, notice the initial rate is of this guy. Okay? So that, and we got that from here. And he's in second, so we don't have to deal with anything. Okay, so the first thing that it wants us to do is to calculate the initial disappearance of BR2 in experiment 1. Okay, this is that question that's usually like the third question that you're going to be like, I don't know how to do this. What did I say? How did I say to set this up? This is the one time I do this. More other people do it all the time, but it's the one time that it's the way that it really helps me make sense. Although you don't really have to do it because they're easy numbers. What it's wanting to know is if we're losing, this is actually we're gaining NOBR, it wants to know what's the rate of disappearance of BR2. Well, you can see that we're losing this half as slow, half as fast. We're gaining this twice as fast as we're losing this.
Yes.
Is that a better way to say it? So the way you set this up is you take the rate, and it's always going to be specific for a specific experiment. So for experiment 1, I have the NOBR is 3.2 times 10 to the negative 4, and he has a 2 underneath him. And we're looking for the BR2, so we want to know his rate, and he has a 1 with him. Okay? And so this answer is 1.6 times 10 to the negative 4 moles per liter per second. Okay? Now, did I really need to do this? Could you not have just looked at it and done it? Probably, but it makes it a lot easier because sometimes you're going to have more than one thing, and it just helps you not get the wrong answer. That being said, what is the rate of disappearance of NO? 3.2, very good, times 10 to the negative 4. They're not going to ask you that, though. Okay, so when they ask you this question, it's about your coefficients. All right, so the next one is determine the order of the reaction with respect to each reactants. Okay, so what we're trying to do here is we're trying to find out, technically we're eventually going to find out our rate law. And so we're trying to find out, and the rate law, the exponents cannot be determined except experimentally. And that's why you have all these experiments. Let's see, if I move. Okay, so, dang, I wish I had like 2 things to show. Okay, so on this one, what you try to do, the first one is you try to find, and I just automatically see this, that, hey, this guy changes and this guy stays the same. So I'm going to solve for BR first. Okay, so on part, well, it's still B. We're still doing B. Okay, so for bromine, and I always just do this to kind of keep track of it. So for bromine, I'm going to do reaction 2 over 1. And so you take your rates. 6.38 times 10 to the negative 4 over 3.24 times 10 to the negative 4, and then equals, now we're at the point that I'm going to, since I'm doing 2 and 1, and NO is going to cancel himself out, and the K is going to cancel himself out, which we don't know what he is yet. I'm just going to quickly do 0.024 over 0.012. Now, those of you really strong in math can probably look at this and say, hey, and they kind of expect you to. They expect you to be able to figure out some of these things. Actually, he's the Y. Just by looking at it, 6.38 second E negative 4 divided by 3.24. This is one time I don't cross multiply because of him. Negative 4. So I end up with 1.96, which is what we're going to call 2, equals 0.024 divided by 0.012, which you can also see as 2 to the Y, so Y equals 1. So now we know that this number is 1. Okay, so now in the next one, I'm going to look for, I need to solve for NO. Okay, they've done this to you again where BR, the reason I also chose BR first is because there is no case where BR stays the same, but we know that he's a 1 exponent. Okay, so we can use him with his exponent. We just have to use the numbers. We can't ignore them on this one. So I'm going to choose who? Yeah, I really don't have a choice. I have to choose 2 and 3, don't I? Well, I could choose 1 and 3. Right. But let's do 2 and let's do 3 and 2, right? So now we're solving for NO. And we're going to choose 3 over 2, and so it's 6.42 times 10 to the negative 4th over 6.38 times 10 to the negative 4. That seems like they're very similar numbers. Equals, okay, I have to plug in my BR, 0.006 over 0.024 to the first, and now my NO is 0.032 over 0.016. Is that going to be a 2? And so I'm solving for my x. Okay, so 6.42 second E negative 4 divided by 6.38 second E negative 4. Okay, it gives me about 2. Okay, and then 0.006 divided by 0.024. Okay, oops, so I'm going to take that other guy because that'll probably push him closer to 2, because he ended up being 1.899 equals 0.25 times 0.032 over 0.016. So 1.899 divided by 0.25. Ew. What the heck is, huh? Here. Let's try, yeah, that's what I thought. 6.42 second E negative 4 divided by 6.38 second E negative 4. Yeah, it's 1. And then divided by 0.25 gives me 4. Equals 0.032 over 0.016. Okay. So 0.032 divided by 0.016 gives me 2. So 4 equals 2 to the x. So x equals what? 2. Yay, we got something besides 1. Also, you might get a 0 or some really crazy number that's kind of like 0. Or something unsolvable, that's 0. So that means then that that reactant is not part of the rate law. So now we can write our rate law. Our rate law is rate equals K NO is 2, right? And BR2 is 1. Now, do not be fooled by the fact that you have a 2 here. Just because you have a 2 here, that's not how we get this 2. Okay? It seems like it will always happen. But this 2 came from an experiment, not the coefficient of this balanced equation. Okay, so the next problem is probably find the K and specify the units. Okay, so I'm going to pick the very last equation. Am I still on the board? So 6.42 times 10 to the negative 4 equals K. NO is 0.006 squared. And wait a minute. Whoa. 0.006 is to the 1. So that's my BR. And my 0.032 is squared because that's my NO. Right? And I'm already going to mess up. Anybody see my problem? I need a 0 here. Okay, so my rate, when I solve all of this, ends up being 104. By the way, we haven't talked about that. That's a really big number. But what order is this reaction? It's third order. Very good. So it's liters squared per mole squared per, and the time in this is seconds. Okay. Now, that rate K is really big compared to 1. So that means that this reaction will want to run to the product side. Okay. Maddie? On how to get a third order? Okay. The order is, okay. Yeah. So let's say we have rate equals Ka, and that's all you have. That's first order. Okay. Second order could be rate equals K, and if you had A and B, that would be second order. You just add up the exponents. Or second order could also be rate K A squared. That's still second order. Okay, we got third order here because we have a 2 and a 1. So our reaction is third order. And so we solve for our K, and they also wanted the units. Well, differential can be ridiculously high. But when you go to do your integrated, the highest where you're really going to work with 0 first and second order. Because after that we don't have an equation, or I don't. So that's kind of a good thing to know. Okay, so we now have the rate law. Now we're going to, and I'll just do it on here. We're going to try and find out if this mechanism is consistent. So our rate law, I'm going to write it down, rate equals K. It was NO second and then BR, right? And our balanced equation, I'm going to write it right here because you can't see it, is 2NO plus BR goes to 2NOBR. Okay, so your mechanism has to meet a couple of criteria. Okay, the slow step has to equal the rate law. Do you understand that the rate law and the balanced equation are not the same thing? Okay, so the slow step has to equal the rate law, and the other thing is that the balanced equation has to, what I call, Hess out, which means, and I'll show you that in a minute. Okay, so my slow step here would mean rate equals K, BR to, oh, also, when you're writing the rate law from a mechanism, you use the coefficients. Now I know that sounds confusing, but that's how you kind of see if it's the same. So there's no 2 in front of this, so there's no squared here. So when you're writing the rate law from your mechanism, it's the coefficients count. Maddie? Like this? It's hard to see like what's, okay, he disappeared. Because like my whole paper's on it. Okay, so right now I'm going to say, hey, doesn't work, right? Rate law doesn't match the slow step, correct? Okay, so this is not a good mechanism. Now the other part I'm going to show you is the part that people seem to have trouble with. Okay, so the balanced equation, which is right here, has to equal this when you simplify it like you do a redox. We already know it doesn't work, but I'm just going to do this anyways. Okay, so this is saying that I have, okay, these two can get crossed out, and this is saying BR2, well, he doesn't need the thingies, plus 2 NOs goes to 2 NOBR. Okay, so the balanced equation does equal, but the slow step doesn't match the rate law. So is this a working mechanism? No. Maddie?
I'm so confused on this.
I know. Okay. I didn't need to do this next step. Do you all understand that we already know the mechanism? Are you kidding me? Okay, now this one's going to get banned in Syria too. Okay. They banned my other one.
Probably shouldn't say.
Yeah, so if I disappear like in the next couple days. All right. Okay. So we know, okay, where do I need to start back on this? Okay. Okay, you have to be this is a mechanism. What it's saying is that this isn't really what happens. What happens is the BR and the NO get together and they make NOBR2, but then the NOBR2 finds some more of this and makes more of this. Okay, so this is how this reaction supposedly goes. If this is really how it works, instead of just seeing this without the behind the scenes, the slow step has to equal your rate law. And my rate law is up here. This is the rate law we figured out. Well, this slow step rate law is one of these and one of these, which is what I wrote here. Well, these two rate laws aren't the same, even though you flip them and there should be a 2 there. But this is squared, and this one did not have 2 NOs. It needed 2 NOs to have a square here, and then it would equal the rate law. Okay. Now, we already know it doesn't work, but it has to satisfy 2 requirements. The slow step has to equal the rate law, and the balanced equation, which is this guy up here, has to equal your mechanism simplified. Is that a better way of putting it? So these two guys, one's on one side, one's on the other. Notice I don't have any double arrows, so I can't do any flip-flopping of the equation. So these two got canceled out, and my balanced equation is 2 NOs plus BR equals 2 NOBR2, which does equal my balanced equation, but we already know it's a no-good mechanism. Does that make sense? Okay. I think it's somebody, why doesn't anyone suggest that I silence that thing? Okay. All right. Is that, okay, that is all we have on there. Did we do B? Yes. We did B, otherwise we didn't get these guys. Now I'm going to talk about an intermediate. In a mechanism, you can have intermediates and catalysts. Let me write it down. Okay, so in your mechanism, I wrote it somewhere. Okay, so catalysts, and you've, huh? Okay, so catalysts are part of your mechanism, and they are consumed and then regenerated. I'm going to show you, this one might have one, it might not. Regenerated. They can be part of rate law. They speed up reaction by lowering activation energy, which we don't know about yet because we haven't done a lot of thermo. Okay, so that's all you need to know about a catalyst. What happened? Oh. Elmo decided to flake. Okay, now an intermediate is something that is produced in one reaction and then consumed in another. So you don't ever see him in the balanced equation. So he's produced and then consumed, and he cannot be in rate law. Okay, now in this particular situation, see we have NOBr2 being produced and then NOB, and then he disappears from our total reaction. Where's our total reaction? Right here, right? So he's nowhere in this balanced equation. So is NOBr2 a catalyst or an intermediate? He's an intermediate. He was produced and then consumed. Okay, and also, one more thing. Rate laws. Only what side of the equation? Reactants. Why? We care about the products, but we don't want. What about the products? Okay. Yeah, it's going to cause us issues. Okay, so you want a rate law to be determined as quickly as possible. And that's why they will also call this initial rate laws. Okay, so that was AP problem, what we called Becca. I think we answered it all, right? Okay. Something's going on with this. Huh? Next is wrong? Oh, yeah, we're not doing Ryan yet. We're doing, I've got a couple of things to show you. Okay. I don't want that. Yes. I'm getting rid of a whole bunch of stuff on here, and then I'm going to put the image mate back up. Okay. So these are going to be fun recordings to painfully cipher through. Okay. So the next thing was 12.1. Okay, 12.1. See if I had room with you guys. Okay. .1 is kind of how your lab is, and I didn't give it to you. I just want to show it to you because it's kind of a lot of work. Okay, so what this is showing, this is like how you would be doing a lab. Let's say you're taking a chemical and he's purple. You add another thing, and then you time how long it takes him to go to clear. That's kind of the reaction we usually do. Okay, so you always start at 0 seconds, and you're at 0 seconds, you have 0 of these two guys because they're right here. But you have a lot, this is the concentration of this guy. So you then take the reaction rate is the change in the concentration over the change in the time. So in this case, this is our change in our concentration, and this is our change in our time. Okay, so if you went and calculated this, which I did, I don't know where that paper is, you're going to end up with this guy. Okay, so this is the reaction rate for 0 to 50. This isn't in your packet. This isn't in your packet because we're not going to do this. Okay, because we're going to be given this. Okay, so this is when they did a reaction, and then the second time after 100 seconds, they measured the concentrations, and lo and behold, they've got less of this and more of this and more of this. So then again, they would take 100 minus 50, which is 50, so that's the change in the time, and we're doing the concentration of this, so it would be the big one divided by the little guy, and that's going to give you this reaction rate. Okay, so that's how reaction rates are found. We are not, if we do this, this is the lab we will do. We most of the time just get the data here because it's almost impossible to do this really well in order to get really good numbers, to get really good coefficients. This is how you figure out a rate law, differentially. Okay, and then the other thing that you would notice on this, by the way, you can take a picture of this later if you need it, is that as the reaction goes on, the reaction rate slows down because you have less of the reactants and more of the products. That's why we really want this part right here. We really don't care about this down here, okay? So I just wanted to show you this. This is how you get those reaction rates, which are usually on the right-hand side of your problems, and they're in concentration per time. This is how you get them. Okay, and these are the times, okay? So, yeah. Any questions on that? I know it's kind of, does it make sense at all to you? Do you understand why we're not doing, that we're just going to be, we're already given this, but this is how it's done. And it's not that bad. Okay, next one. Okay, I have 12, okay, that was 12.1. Let's do the homework. And then I've got one I labeled 666 so that I can find it. Okay, so the homework, the one, when I say homework, it's the paper that looks like homework. Here it is. All right. If I have an extra copy, I think I'm going to cut out the little problems and put them on top of each problem when I'm working it. Does that sound like a plan? We've got the time, right? We got to learn the rest of what? Yeah. Yeah. Really? Have we already had an hour go by?
Yeah.
Well, 40.
Time flies when you're having fun, right? All right. So, I'm going to... No. You have a quiz tomorrow. I don't know. We're running out of time. I don't know. We'll just have to see. Okay. Now I need some white paper. Okay. So the first problem. Okay. Okay, so this is the one I'm going to cut on. All right. So this is that question that's usually like the third one. Who's singing? This is the third one that is usually in a problem, and it says if you have an experiment, we have. Oh, it's also kind of tricky, kind of mean to you. Over time, we're going to consume 0.0048 of this guy, but he's in a 2-liter container. And so it wants to know the rates of P4 and hydrogen, what's it called, being produced. Okay? So the first thing you've got to do is solve for your rate. Normally you don't have to do this, but it's 0.00, change in concentration, 0.0048 over 2 liters. And it doesn't tell us their time, so I'm just going to have it be a T. So it's going to be 2.4 times 10 to the negative third molar per, let's just put seconds, it's easier. Okay, so that is my rate. That is the rate that the pH3 is disappearing at. Where am I getting the 2 and the 2? Isn't it this divided by this? Yay, nay. Well, I would hope so. That's what I have written down.
Do you not put liters in this?
Liters is in this. This is moles per liter. Okay. All right. So now it basically wants you to do ratios. Okay. So the rate of P4, let's do the rate of P4 first. So if pH3 is at 2.4 times 10 to the negative third, but his coefficient is a 4, my P4 is x over 1. Okay, so that's my P4. Okay, so when you do the math for this, your P4 rate of appearance is 6 times 10 to the negative fourth moles per liter per second. Okay, and then the rate for the hydrogen, I'm still going to go off of my pH3, which is 2.4 times 10 to the negative third over 4, because of that 4, equals, and the hydrogen, x over 6. Okay, you see how to do these? And why, if it's 1s and 2s and 1s to 1s or 2s to 2s, you don't have to do any math. But with this, it's kind of a little, some of you can actually see what it might end up being. But so this ends up being 3.6 times 10 to the negative third moles per second for my hydrogen. This is my P4. Okay? These aren't hard. Do you understand the concept? Okay. All right. The hardest part, or actually the mean part, was that they put it in 2 liters. So you had to actually, molarity is per liter. So you had to start out dividing this. Okay? So the next problem that I have is 18. Okay, I want to do 18 because this is actually maybe I should have done 18 first. Okay, this is what I'm trying to get explained to you. Okay, so it wants the relationship between these rates. So you've got this written equation here, and so the rate, am I on the board? Yeah, good. Okay, so the rate, now what are N2 and H2 doing? Are they increasing or decreasing? They're going away. And what is the NH3 doing? He's gaining. So technically the rate of N2 and H2 should be negatives. Okay, so I'm going to start with the NH3. So the change in the NH3, because he's positive, over 2 times the change in the time. That's the same thing we're doing up here. Okay, and that is equal to the change in the N2, but he's negative because we've got to make, because the change in the concentration will be a negative, so we have to put a negative in front of it to make it a positive, because you can't have a reaction rate that's negative. Just like you can't have negative meters, right? Okay, so my N2 gets just a change in T because he is just an N. And he's equal to the negative change in the H2 over 3 delta T. Okay. This is a very important concept right here. It's not hard. Does it make sense? You've already been using it up here without maybe realizing it. Okay, Maddie? Yeah, because if you did the change in concentration over change in time and really did it, you're losing these, so it's going to be a negative number. So we don't want a negative number up in our reaction rate, so we just put a negative here in order to make it a positive in the end. Because they're on the reactants and they're going away. We're losing these guys and gaining this guy. Okay? Okay, next one that I'm going to do is 19. I might skip. Do I need to do 19 with you all? It's reaction. You're going to do them anyways later. Okay, so 21 is next. Okay, this looks lovely. Okay, 21. Okay, so let's put 21 right here. All right, so, okay, now they're looking at the chlorine being the one that they chose to. You can choose any one of your things to be the rate law, so that means that this right here is about the chlorine. Okay, I don't think it necessarily matters, it's just really good to pay attention to that. Okay, so what's the question? Oh, I cut off the question. What's the rate law and what's the value of the rate constant? Okay, so rate law, and when it says what's the value of the rate constant, what are they referring to? K, very good. Now, our rate law is rate equals K, NO to something, and Cl2 to something. We don't know what they are yet. All right, so let's look at our problem. You want to solve for Cl first? Because I see right here, he changes and these two stay the same. So I'm going to put equation 2 over 1, and I'm solving for Cl2. And just, I always put the reaction rate on this side because that's what this is, and then these guys over here. So it's going to be 0.36 over 0.18 equals 0.2 over 0.1, and these guys get canceled out. Okay, so that ends up being 2 equals 2 to the y, so y equals 1. So now we know this is 1. Okay, now for the next one, I'm going to look at these two guys change and these stay the same. Okay, so I'm going to do equation 3 over 2 to solve for my NO. Okay, so this ends up being 1.45 over 0.36 equals 0.2 over 0.1 to the x. Okay, and that ends up being 4 equals 2y, or x, sorry. So x equals 2. Okay, by the way, if you increase a reaction by 10 degrees, you double its rate. If you decrease it by 10 degrees, you decrease it, you half its rate. And those are good things to be able to know. We'll learn about those more later. You will be able to look at rates and tell whether or not they're doubled or what rate law they are. Just a little aside, I had a student whose dad works at UT working in, I guess it's in microbiology. Anyways, what he's studying is, and he's got it on the screen, and it's this beautiful cell. And so when I just said that if you increase the reaction by 10 degrees, you double its rate, or decrease, blah, blah, everything does that except mitochondria. You change the temperature, the mitochondria don't change. And that's what he's studying and trying to figure out. I wasn't on. You know why? The thing is he's studying everything. When you change the temperature, you change the reaction rate, except for mitochondria. So they're trying to. Well, I wasn't going to say that on here. It's maybe a joke. Maybe that's where it came from. Okay, so are we done with this particular problem? No? Oh, we have to solve for K, right? All right, so I'm going to pick the bottom equation so that it's easy for me. So I'm solving for K, so rate equals, so I'm basically going to plug in things into this. So 1.45, and it's moles per liter per minute, equals my CL, which is 0.2, and it is a 1, and my NO, which is 0.2, and it is a 2, right? So, oh, and these are brackets actually, and so those are moles per liter. That's what the brackets means concentration. So when I divide this by 0.2 divided by 0.2 divided by 0.2, I end up with K equaling 181. Now, these two can cancel off. To get rid of this guy, I have to do liters per mole over here and liters per mole over here, so that these guys cancel out. So I end up with, I should end up with liters squared per mole squared per minute. What did I do? Why did I not get that? Oh, because this is a square here, so I actually have two of them. Okay, so that's why I ended up with, so I had to do two of these to get rid of them. Okay, so to get rid of both of them, so I end up with that. Okay, how did I know that it was going to, how did I know I went awry? Because I know that, what order is this reaction? What? Third. And so if you kind of know that it's going to be a flipped molarity to the second, and it goes down from there. Okay, so does this reaction run pretty much to completion? How do you know? Your K is pretty big, okay? So that means that this reaction is going to lay on the product side more than the reactant side, okay, when it happens. Okay, that's the only way we know this, because we're not running anything to see what the reactant products are. Okay, are we done with this problem? All right. Okay, so that was 21. Let's do 23. I got a star next to 23, or 22. I swear. All right. Now, a smart person would like staple those to these pages and label them. But I like boxes of chocolate. Okay, so 22. Okay, we're getting into some more fun. Actually, this was for the other guy, so we're going to get rid of him so he doesn't confuse us. Okay. All right, so this is now a little more interesting. What's it want? It wants the rate law, and it wants the rate constant K for, and then an average rate, okay? And I put down for B, no, we're not doing that. They want us to like add all these up and divide by 1, 2, 3, 4, 5. I guess we could do it, but we're not. Okay, so determine the rate law. Okay, for this one, for me, I looked at experiment 1 and 2, and SO2 stayed the same, but the I changed. So, and then I also looked, and in this case, I'm not going to flip the reactions. You notice, remember how I normally flip the reactions? But I want a whole number here. Hold on a minute. Let me look at this. Oh, I'm looking at the wrong problem. The next one's going to be even more fun. Okay, so I'm going to take 12.5 times 10 to the negative 6, and then 6.25 times 10 to the negative 6 equals, I'm going to ignore the S206, and I'm going to put 0.08 over 0.04, and this is just to my x. Okay, so 2 equals 2 to the x, so x equals 1. Okay, so we know that this guy is to the 1 right now. Alright, so now we're going to do it for the S208 minus 2, whatever the heck that thing is. Okay, and that, I'm going to look for a case where he changes and hopefully the I stays the same. And the one I'm seeing is 1 and 3. Okay, so I need these two. Okay, so, and I'm going to look at this. I'm still going to put the top one on top. 12.5 times 10 to the negative 6 over 6.25 times 10 to the negative 6. That's going to be a 2, right? And then 0.04 over 0.02 to the y. So that's going to be 2 equals 2. So y equals 1. All right, now, so my rate law is different than my equation. Rate equals k. The I is just, I minus is to the first, and the S208 is also to the first. Okay, so what order is this reaction? Second order, very good. What order is this reaction in regards to the I minus 1? First. And it's also first in regards to the S208 minus something. Okay, so then what's it want? Determine the rate law. Okay, so we know how to do that, right? What did I tell you to pick? The bottom one. Because otherwise you're going to put numbers, you're going to be all over the board. Equals K, 0.06. The hardest part is, if you do have exponents, keeping the exponent with the one he should be with. Okay, so I ended up with that. And so my K equals about 4. 3.89 times 10 to the negative third liters per mole per, and my time is seconds, so seconds. Okay, now, I didn't show you all of the crossing out of the units. You can memorize that, or you could do it when you actually have to deal with it. Okay, so that one was pretty easy, right? Hello.
You came to my loft for the building.
Okay.
Could I get your name so I could get you a ring key?
Sure. Smalling,
Okay.
Julie.
All right, I'll be right back.
great. Now I'm on here. I've, are they changing them to everything?
Yeah.
Okay, because I need one to the chemistry prep room.
Okay, we won't get that one today, so hold on to that key.
Okay.
And then I can get you a key one.
Okay, thank you.
Yes.
All right, thank you.
Oh, you're welcome.
Okay. All right. That was number 22. Don't sound so excited. We're almost done. 23 we got to work on. Okay, so I'm going to move this guy. Do 23. We'll eventually get this perfected, right? Okay. So 23. Equation looks familiar again. Okay, so following data, and notice I wrote on mine just so that I could kind of keep it straight. This is my reaction rate, and this is my concentration of this guy. Okay, now he's in a different kind of unit. He's in molecules per cubic centimeter. And they're just going to make us do some factor analysis for fun. Okay, so the first thing is, what's the rate law? Oh, okay, yeah, this one you got to pay attention to. Okay, so I'm going to take, since I only have one reactant, I'm going to just do, let's see, I did equation 1 and 2 so that I could keep it straight. So 1 over 2, and I think I'm going to do this on purpose this way. So 5.98 times 10 to the 4th over 2.66 times 10 to the 4th equals, got to keep them straight, 3 times 10 to the 16th over 2 times 10 to the 16th. Now you could kind of get rid of those, but okay, and these are the reactants, so they're to the x. Okay, so when you go to solve this, you're going to end up with 2.25 equals 1.5 to the x. Yuck. Okay. What you could do is punt this one and go and try and find one where these guys are going to work, but if they're all the same, they're all going to come up with the same number for your rate law. So what you do for this is you make them into logs, and I'm going to skip a step, but I'm going to do log of 2.25 equals, and then I'm going to pull this guy down, x of log of 1.5. Okay? Those of you in calculus, let me know if I'm missing something yet. Huh? And so now I'm going to take this guy and move him over here, because for some reason with logs, and subtracting them is really dividing them. So I'm going to take log of 2.25 over log of 1.5, and that's going to equal my x. Okay? And so then my x, when you do the math, equals 2. Okay? All right. Now, so now we know that our rate law is rate equals K NOCl 2. Now, let's say you were in a pinch and you had like 2 minutes left to write the rate law. if it were me, I'd be like to the second. If I was running out of time. Do you know what I mean? It's like 90% of the time it's going to work. Mikhail, wake up. Okay, so the next thing is calculate the rate constant. Easy peasy, right? So I'm going to take, so this is B, 1.06 times 10 to the, shows true life, I guess, right? Equals K, and then 4 times 10 to the 16th. So my K equals, and I'm showing this one because he's not normal, is 6.625 times 10 to the negative 29. But he is, okay, what, my rate law is second order. Okay, so I have to flip this, so it's centimeters cubed per molecules per time. Rate, K is always going to have time in it. Okay, so now that's my rate law, and now it wants to calculate it per moles per liter. So 6.625 times 10 to the negative 29 centimeters per molecules per time. Okay, so it wants moles per liter. So there are 6.02 times 10 to the 23rd molecules in a mole. And then I have to actually do this 1,000 centimeters cubed in 1,000 milliliters, which is 1 liter. Okay, so when you do all that math, you end up with 3.98 times 10 to the negative 8 liters per mole per time, which I left way down there. Okay? Yep. Yeah, I'll be busy cutting out another piece of paper that I can't find. Where'd it go? Ah, here it is. Okay, so the next one we're going to do, let me see which one I want to do. Is this getting easier to you? You guys feeling a little more comfortable with it? Okay. How about I leave, you may have not done it, so let's leave 24 for you guys to do. Actually, did we just not do? It's the same reaction. Let's look at 25. We only have 2 more to do, and then we've got 666. Let's do 666. And I'm going to leave 24 and 25 for you to look to do on your own, because I'm pretty sure probably you haven't done some of these, right? So can you do 24 and 25 now? Like, not right now, but now that we've done them. Okay, so I'm going to leave those 2. And I wanted to work on okay, I did 12.1, I did Becca. I think it was a problem in your actual packet. table 12.1.